Hello and welcome to section 5.5. We're going to talk a little bit about the difference between enantiomers and diastereomers and how to detect a diastereomer. So first, let's go back and remember just a little bit about what we talked or how we defined what an isomer was. Remember that isomers are molecules that have the same substituents or parts connected in a different way somehow. And of the isomers, we already knew about constitutional isomers, the ones that had the same molecular formula but different connectivity. And we also learned in section 5.2 about enantiomers, which are non-superimposable mirror image molecules. But in this section, we're going to learn about what are called diastereomers. Those are non-superimposable, non-mirror image molecules. So what exactly does that mean? Well, why don't we start with this small example here. This molecule. There we are. Okay, so if we were to draw this molecule's its enantiomer, remember we need to start by drawing a mirror plane and then drawing the mirror image of this molecule, right? So now the chlorine is on a wedge, hydrogen is on a dash, and this hydrogen is on a dash. Okay, and this CH3 is on a wedge. There we are. And this is the mirror image molecule. And remember, in its definition, we said that well, we said that it is non-superimposable, right? And that's what it looks like there. Because if we were to turn this around, we can't turn this around and have it be the same exact spatial connectivity there, can we? So that's what makes it a non-superimposable mirror image. But since that is the enantiomer, we'll just label both of these E. Does this molecule have any diastereomers? Okay, non-superimposable, non-mirror images. All right, so then let's draw the same molecule. Let's start from the one we just drew, the second enantiomer. All right. So we'll put the hydrogen on a wedge here again, and the CH3 on a dash. But this time, let's change up where the hydrogen and chlorine are. Okay. And if we do that, and we have a look again, first, let's check if these are superimposable. And it looks like they are not. Yeah, they are not superimposable because if you flip it over horizontally from left to right, the hydrogen on the bottom would be in the correct place, but the hydrogen on the top would not. Okay, so it's non-superimposable. Is it a mirror image now? So we bring it over to the mirror plane, and we decide that no, it's not a mirror image. If you need to see that closer, we'll grab this, and we'll move it away for a second. There we are. Move this one over. So now you can see, hopefully much clearer, that the chlorine, hydrogen at the bottom, they are not mirror images. So now this molecule is a non-superimposable, non-mirror image of the other. which makes it a diastereomer. Let's move this back up. We're supposed to go. There we are. So there we are, your first diastereomer. So that makes this one not only a diastereomer, but it makes our original both an enantiomer and a diastereomer. It means that these two are diastereomers and these two are enantiomers. But the first and the third structure are not enantiomers, and the second and the third structure are not enantiomers. Because each pair of enantiomers is a diastereomer with the same structure here. Oh, actually, this is a diastereomer too, right? Yeah. Okay. Great. So something kind of funny happens because you see that there can be many types of diastereomers for a molecule, many types of non-superimposable, non-mirror images. And it turns out that the number of diastereomers you can have follows a very simple formula, which is 2 to the n, where n is equal to the number of chiral carbons in the molecule. So as you get the more chiral carbons, you end up with more and more possible diastereomers. All right, so let's do a little practice, finding out if something is an enantiomer or a diastereomer, or if a pair of molecules is an enantiomer or a diastereomer. All right, so we have these two molecules. Let's determine if they are enantiomers or diastereomers. So first thing to do is to make a mirror plane between the two. All right, I'm just going to move these real fast. There we go, just so it's a little more comfortable. Nice. Okay, there's a mirror plane now. And you have to ask yourself, are these mirror images? Move a little closer. I think it's not a mirror image because if it were, the two carbons here would be on a dash, right? So then they're not mirror images. And the question is also, are they superimposable? They don't seem to be superimposable here, right? Or are they? Because what if instead of doing that, what if we now flip this molecule over? Right? What if we, let's redraw this. What if we kind of act like we're flipping a pancake? We flip it right over. I think what you'll find is we make this molecule if we flip it over. We'll say that's a flip. So then that's the same molecule that we just had before, right? So since that's the case, they are not enantiomers and they are not diastereomers. They are identical molecules. All right, there's one more structure here. And it looks like this is the molecules, the pair of molecules that we're dealing with here. And at first glance, it looks like these aren't even isomers, right? Because it's it's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, Is that 5? No, 5 is down here. Oh, okay, they are isomers, right? Because there's a methyl on 3 and 4, just like before. So you have to be careful that when you're looking at pairs of molecules, that you are making sure that you are recognizing if they can be stereoisomers or if they're not isomers at all, because of like carbon count or molecular formula or something. Because in both cases here, they have the same molecular formula if you're not seeing it. That's 6, 7, that is a hexane, or that's a hexane with 2 methyl carbons. That's C8. That's 3, 5, 6, 9, 12, 13, 15, 18. And this one is also 8 carbons. H, 3, 5, 6, 9, 10, 13, 15, 18. So they have the same molecular formula, so they can be stereoisomers now. Or they can be constitutional isomers, but we see that they have the same connectivity, so they cannot be constitutional isomers. All right, so what we need to do in this case is we need to find the relative configuration in CIP format of both of these chiral carbons. And hopefully you see when I say both that I mean this carbon and this carbon in both cases, the carbon 3 and 4 carbon. Okay, so looking at what we'll start with on the left. So on the left, we have 4 substituents, right? So we need to assign priority. So hydrogen's 4, obviously. And then we have 3 other substituents. And it looks like we're going to have to do a tiebreaker. Okay, so the substituent on the left, middle, and right. So the substituent on the left has 2 hydrogens and 1 carbon. The one in the middle has 3 hydrogens. And the one on the right has what looks like 1 hydrogen and 2 carbons. All right, so it looks like the one on the, no one has 3 carbons, but the one on the right has a second carbon, or doesn't have a second hydrogen, which means it is number 1, right? That's the highest priority, and then the second highest priority looks like it's the left. So that'd be 2, and 3 is the middle. So then we make our Newman projection on that carbon there. And when we do that, we end up with, let's see, this was CH3 going up. To the left was ethyl, ET for ethyl, and to the right was the this group here. And again, remember this was 1, 2, 3, which means we rotate this way, which is R. Okay, so we have R for the second one, or for the first carbon on the left. And on the other molecule, it looks like that carbon has the same configuration. So that's also R. Okay. Now for the second carbon here, I'm going to erase some of this so we can rework through the same progression. There we are. And remember, we just said that this is R. Okay, so in the second chiral carbon on the left, we have 1, 2, whoops, 2, 3, and 4 groups, right? There we are. Hydrogen always gets the lowest priority, number 4. There we are. Okay, it looks like let's do a tiebreaker. We'll do left, middle, right again. Great, so it looks like the middle one has 3 hydrogens. The right one has 2 hydrogens. And the left one has 1 hydrogen. All right, so that means that it looks like the left one is number 1. The middle one is number 3 because the right one is number 2. And we found that, if you remember, because the left had only 1 hydrogen, the right had 2, and the middle had 3. Okay, so then when we make our Newman projection, oh, we can make our Newman projection, can we? Because hydrogen is not on the dash. So now we need to make hydrogen be on the dash, and I suggest we hold the left, the number 1 priority thing constant, which means if we redraw this, there we go. It's a CH3 up there, and okay. Oh wait, that's not right. Okay, so now we're gonna twist the 432 to get the hydrogen on the dash. So if we do that, that means that on the wedge becomes the ethyl group there. There we go. On the dash becomes the hydrogen necessarily, and the methyl group goes on a normal bond. Okay, so now doing our Newman projection on that carbon there. We have, so here's our Newman projection, and it looks like we have a little different, it's laid out a little differently this time, but that's okay. We have number 1 there, because remember that was number 1, that was number 2, and that was number 3. So 2 is here, 3 is there, and we go R. All right, so we have 2 R's in this molecule. I need to erase this stuff here. That way it makes it easier to see. There we go. So then there's RR. All right, and then last, we're going to have a look at the second carbon on the right to see if it's the same or not. Okay, so once again, the second carbon. How many substituents do we have? We have 1, 2, 3, and again, this hydrogen on the wedge makes 4. Okay, so that would be the fourth one is, the 4th priority is hydrogen, of course. And just as we knew from before, the tiebreaker, the CH3 in this case is going to be the 3rd highest, The CH2CH3 is going to be the second highest, and the CH3, CH2, CH3 is going to be the number one highest. Doing the same tiebreaker as before. I didn't write it out this time, but you can find that for yourself as well. So we need to do the rotations to make this molecule to find the hydrogen on the dash as we did before. So redrawing this molecule. There we go. It's CH3 there. So now let's rotate to get the hydrogen on the dash, which means that this time the CH3 is going to be there. The hydrogen will be on the dash, and the ethyl group will be on a normal bond, which means when we do our Newman projection, looking at this, then we will have that same slightly different layout as we're used to seeing. The CH3 here, the bigger group that was number one, we'll just do them in their, we'll draw them in their priority groups, because remember the bigger one here was number one, the ethyl group was 2, CH3 3, and H4. So then that would be 1, 2, 3 there. So then we have clockwise rotation, which makes it R. I think the second one was actually S. The one we did on the left. I think that one was actually S, right? Yeah, it was actually S. I got that wrong. I'm sorry. I don't know where my mind was at. Because if you do the rotations again on the left, just so that we're clear, do the rotation again on the left, then you have the ethyl group there, hydrogen going back, CH3 up. Yeah, that should have been S, because the Newman projection here. We'll do the same thing. That was 1, 4. Three, 4, 2. So then 2 is on the bottom. 1. Yeah. And 3. So that's counterclockwise. Should have been S. Okay, great. So now we see that one is RS and one is RR. And because they are then non-superimposable, non-mirror images, being two different CIP configurations, then they are diastereomers. This has been section 5.5.